Excellent. Okay, so yeah, in this talk, I'll talk about a couple of papers. So the first one's on subsystem codes. I have given a talk on this at a couple of conferences this year, so apologies to anyone who might have seen some familiar slides. But I'll be adding in some more details on the scheduling aspects of that work. And feel free to ask questions throughout. And also talk about some work on encoding circuits. And both of these are published this summer and on the archive last year. Okay, so this was joint work with Nico Breutmann at UCL. And the motivation is, can we beat the surface code? And so there are many challenges associated with the surface code that we'd like to overcome. So one is the huge overhead of around 1,000 physical qubits per logical qubit. Another is that wait-for checks can be too large for some systems where crosstalk can be a problem. There's been work at IBM looking at subsystem codes that can reduce the degree of the interaction graph for that. Thirdly, the hardware is currently still above the threshold, so we'd like to improve on that. Finally, the square surface code isn't optimized for biased noise models. We'd like to look at codes that can potentially do better under biased noise models. Mm-hmm. And so for reducing the overhead...
Can I already ask a question? Sorry, I will not ask too many questions, but maybe a quick one. When you say overheads, I mean, you mean overheads for the full computational scheme, like including magic state distillation or lattice surgery or so on, or are you just referring to storage as such?
So we're interested in reducing the overhead for all aspects, although in this work we focus on storage. But yeah, excellent question. Yes, we definitely need to focus. Yeah, work needs to be done on all aspects. And I guess the question of interest is for some given application, some given quantum algorithm, what are the total time and space resources and overheads? But yeah, for this work, focusing mainly on storage.
But in this work, you also, I think I vaguely remember from your paper that you also do count in ancillas, right? That you need. So it's not just data qubits.
Yes, that's true. Yeah, we count ancillas for circuit level noise. And so, yeah, so I guess often, yeah, so I guess it brings on to this slide. So for reducing overhead, a lot of the work is focused on new quantum LDPC codes. And so with these, with improved theoretical parameters like hypergraph products, hyperbundle and nifty products and balanced product codes. And so, yeah, these have theoretical parameters, but they're difficult to schedule with and have high weight checks, so they can lose their advantage for circuit level noise. And so, yeah, I guess I'll get onto it later in the talk. But yeah, in answer to your question about ancillas, we do include ancillas and consider circuit level noise. So kind of making steps towards what's needed to demonstrate that LDPC codes can be used with a reduced overhead compared to the surface code. And then other prior work on higher thresholds. So for bias noise, there's been a lot of work recently on the XZX and tailored surface codes, which have high thresholds for bias noise, but they still have the wait-for checks, which can be bad for crosstalk. And actually, it's still not clear what's the best approach for below threshold, even compared to the surface code. And so in this work, we look at reducing both the check and the qubit overhead relative to the surface code for storage. And so we introduce finite rates quantum LDPC codes with 3 qubit check operators and show that these outperform the surface code under circuit level depolarizing noise. And also show how to improve the thresholds, especially under bias noise. So it's a new technique for decoding subsystem codes that can be applied quite broadly to other subsystem codes, but we apply it to the subsystem surface code. And that uses gauge fixing in software to obtain more useful information. So a brief recap on subsystem codes for those that aren't familiar. So subsystem codes are stabilizer codes where a subset of the logical qubits are not used to store information. And they're defined by a non-abelian gauge group, and the stabilizer group is at the center of this gauge group. And in some subsystem codes, the gauge operators conveniently factorize the stabilizers. So you can measure a stabilizer by taking the product of the gauge operators. And therefore you can measure the low weight gauge checks and then more results to infer the stabilizers. So it can simplify the stabilizer measurements. And our work focuses on generalizing and improving the subsystem surface code. So I'll just introduce that here. And so here qubits are on vertices in this lattice, and each of these blue triangles is a Z gauge operator, and each red triangle is an X gauge operator. And then the Z stabilizer is the product of the two Z gauge operators on the face, and the X stabilizer is a product of each X stabilizer is a product of the two X gauge operators on the face. Now we generalize this to hyperbolic codes, hyperbolic tessellations. And so here we end up with stabilizers of weight 12 and gauge weight 3. And so all the check operators now are weight 3, and we have an improved encoding rate. So now the number of logical qubits scales with the number of physical qubits into family. The distance is logarithmic in N, and so KD, the ratio KD squared over N, which you want to be large, scales at log squared N, and that compares to, say, it's a constant for the surface code. So the theoretical parameters are an improvement on the surface code. And so in this way, we're looking at ways to make it, see if we can retain that improvement in practice or with circuit noise.
Right,
I have one question there. Sorry, it was my fault that there was this feedback because I turned on the microphone. So your parameters in the scaling of the distance and the encoding rate, is it different to the non-subsystemized version? No, right? Because at least the distance should be the same as the normal hyperbolic code.
Good question. We'll come on to that in one slide. So I will, I'll come back to them.
I see that applies both to the hyperbolic codes and to the semi-hyperbolic codes.
Yes. Yeah.
Okay.
So I'll answer your question on the next slide after this one.
Maybe also briefly recap like how exactly you set up this construction here. Like you take a hyperbolic plane which is tessellated, and then you identify these corners, right? And then every like the X and Z stabilizers are just the corners, like the product of the corners that belong to the same face.
Or... Yeah. Sorry. Yeah. So in each face, so let's say you take this face. You take the product of the 4 weight 3 gauge operators in that face, and that forms a weight 12 stabilizer. And the lattice has to be D4 to ensure commutativity, and an even number of edges for each face.
Mm-hmm. And it's of course negatively curved, right? Well,
yes.
So the Schläfli symbol, if you want, would be sufficiently large so that you really get a curvature out.
Yes, exactly.
Mm-hmm.
Yeah.
But the product of triangles around a given vertex don't have any meaning, do they? Or like, I mean,
no.
Okay.
I did warn you that there would be many questions. So
no, good.
Sort of the generalization of the Venn plaquette model for the surface code.
Yeah.
Okay.
So where you have the qubits on the vertices instead of the edges.
Ah. Right. Okay. Cool. Yeah. Makes sense.
Okay, we also consider semi-hyperbolic lattices. So here we tile each face with a square lattice of a hyperbolic. This has been done before for stabilizer or subspace codes. And so this is useful. Well, I'll explain the construction first. Yeah, you tile each face with a square lattice, and then you take the dual of this lattice. So you exchange faces and vertices, and that gives you a lattice with the parameters which allow you to construct a subsystem semi-hyperbolic code. It needs to be degree 4, which is why you take the dual. And this is useful as it then gives you a family of codes which scales as a square root of the number of the distance scales as the square root of the number of qubits as you fine grain the lattice. And so you can kind of retain an advantage in qubit overhead reduction once you've increased the size of the hyperbolic lattice. And then you can further reduce the logical error rate exponentially by sort of fine graining the semi-hyperbolic lattice. So that's the motivation behind using these semi-hyperbolic codes. Okay, now onto the distance, which answers your question. So you do have to be careful with subsystem codes because multiplying integrals by the gauge operators can decrease the distance, and that's called the dressed distance once you multiply in the gauge operators. And so the dressed distance of the subsystem hyperbolic code, we show that is at worst half that of the stabilizer code derived from the same tessellation, and at best the same. So there's an upper and lower bound. And that's shown by these reds, and the red and the green lines. So the red line is the upper bound, and the green line is the lower bound. And so this is showing a subspace code distance, and then the y-axis is the subsystem code distance from the same tessellation. And it kind of spans the full between the upper and lower bound. So you can just take the codes which are lie nearer the upper bound. So yeah, the distance can suffer, but by at most a half.
So did you find the plot by exhaustive search through the group for these smaller codes?
So that we prove the upper and lower bounds, and then these blue circles. Yeah, this is just all of the codes that we were constructing of this particular family, and you can use sort of Dijkstra's search because they're 2D codes. You can use sort of shortest path searches to find the minimum distance efficiently.
I see, but you do it explicitly for each.
Yeah.
System size. You have no analytic expression or anything similar.
Yes, exactly. Yeah. So for each lattice, for each compactified lattice, we construct a code, and then it finds we don't. Yeah. I guess we don't compute it from, say, the representation of the group. We construct a lattice and then do a Dijkstra search. Yeah. Maybe there's a more efficient way, but it's already quite efficient just like that. So, so each of these blue cycles is just so there are 54 codes in this that have these parameters that we found. Yeah, so these are all constructed explicitly.
Cool, thanks.
And that it's bounded by half the at worst half that of the stabilizer code. Is this obvious, or did I miss this?
Yeah, I didn't explain why that's the case. I don't know if I got a figure that will explain that. You can think of it as, okay, so intuitively, if you imagine a logical case, say, coming down diagonal. So in the subsystem surface code, the distance isn't reduced at all, just because of how the logicals line up. But if you imagine, say, a logical coming down here, then applying this gauge operator will reduce the weights. You can turn, if you apply this gauge operator here, if you apply all the gauge operators in the worst possible way, then you're reducing the weight of the logical by at most a half. But I guess you can think of it as if you take any shortest path through the lattice,
okay,
then applying the gauge operator will reduce the weight of that by at most factor of 2.
Okay, yeah, that makes sense. Okay,
but I mean that's the worst case. And so in the surface code, it doesn't reduce at all. But yeah, almost 2.
Okay, thanks.
Okay, now an important question is how can you schedule these codes? And this is a problem that a lot of LDPC codes suffer from because they're often randomized constructions with high weight stabilizers. And so constructing an efficient schedule is quite challenging if you measure the stabilizers. Now for the subsystem toric code or surface code, it's translationally invariant, which makes it much more simple to schedule. So yeah, the subsystem toric code schedule is translationally invariant. And so each triangle operator has one of 4 possible schedules. So I've labeled this on the right here by different elements of Z4. And so I'll explain why I'm describing it in this way, because it will help us generalize the hyperbolic tessellations in a minute. But we can label each triangle operator that shares the same schedule with the same elements of Z4, as so. And we can also consider the orientation preserving symmetry group. So this is a subgroup of the symmetry group of the square tessellation generated by rotations around faces and vertices. So got a rotation rho around each face and sigma 180 degrees around each vertex. This is the presentation of the group with the relations rho to the 4 sigma 4 and rho sigma squared of the identity. And this is useful because we can now identify each triangle operator with an element of this group. So one-to-one correspondence once we define the identity. The mapping of the identity. So why are we doing this? Well, this defines now a group homomorphism from the orientation preserving symmetry group of the tessellation to Z4 with this definition. And why is that useful? Well, because the hyperbolic tessellations aren't translationally, they don't have translation invariance, so we can't use that. But what we can use is the group structure of the tessellation. So for some tessellations, such as the 8-4, 12-4, basically any 4K4 tessellation, we can find a group homomorphism that maps from the translation of the orientation preserving symmetry group to Z4. And then we can, what we show is that by doing this, we can use exactly the same schedule as for the subsystem surface code. So let's say we have a schedule for any triangle operator labeled 0 in the subsystem surface code, we can use exactly the same schedule for the triangle operator labeled 0 in this subsystem hyperbolic surface code. And so although we don't have translation invariance, we can use the symmetry of the lattice to schedule efficiently. And so that means we only need a depth 4 circuit to measure the stabilizers of the code. So yeah, so subsystem hyperbolic code has an efficient schedule if the proper symmetry group emits this group homomorphism. And so for each relation R in the presentation, we require that f of R equals 0. And so this does restrict us to 4K for hyperbolic tessellation. So the commutativity condition already limited us to 2K for, so even R in these Shapley symbols, but now it limits us to multiples of 4 for the scheduling to work.
So you get like a constraint on possible tessellations of the plane from like proper symmetry group requirements. Is that the case?
Yeah, exactly. Yeah.
It's kind of okay.
Okay, but so on the wait, sorry, just let me try to get this right. On the okay, I'm still trying to figure out what I'm trying to ask. So for the scheduling, you know that it is optimal. Is that
yes.
Yeah. Okay. So
optimal in the sense of the depth, just because essentially there are no idle time steps. So it's optimal in that sense.
Okay, and everything is completely parallelized, but you still have a separate, I mean, you still have separate schedules, like you do not interleave X and Z checks. Like you do some X checks and you do like Z.
No, they're interleaved.
Oh, they're completely interleaved.
Yeah.
Okay.
Because you have always you have 4 adjacent triangles that might overlap, right? And half of X checks, half of them are Z checks.
Oh, but the
blue
split.
and red colors.
Right.
So
oh, right. Okay.
Okay.
Wow. Yeah. Right. So okay. So the only way that they're split is by these labels, and this labeling does incorporate, like, is set up in a way that it does like satisfy. I mean, we called this at some point like this the corner constraint, like like when you like overlap X and Z checks, like you have these, like there are these special things you need to take care of when you overlap them, because otherwise you will accidentally measure like the Z ancilla in the wrong basis and this kind of stuff. So this is built into these.
Yeah. So the way to think of it is that it doesn't necessarily give you the actual circuit, but it shows that provided you have a circuit that is valid for the subsystem toric code, you can use exactly the same circuit and you'll know it's guaranteed to be valid for the subsystem hyperbolic code. Essentially, locally, if you look at any local region, it will be identical to a local region of the subsystem toric code. So that's the motivation behind this. So it's just a way of, when you've got translation invariance, you only have to worry about some small patch of the code and schedule that. It's a kind of a similar tool. We were just saying, well, given this homomorphism, you have to worry about finding the schedule in some particular parts, and in particular here, you can use exactly the same schedule as you use for the subsystem toric code and just apply it.
So yeah. So this is why this is very smart. Yeah, nice. So this is why you need S equals 4.
Exactly. Yeah.
That's good.
But even then, you still have to worry about the compactification. So in order to form a kind of a compactified, a closed surface, you also add in additional relations to the group, and so these also have to satisfy this constraint f of R equals 0 in order to admit this homomorphism. So it's for a subset of 4K, 4. Yeah, 4K 4 RS relations. We find empirically it's around half of them half factorified lattices admit the homomorphism. We don't. Yeah. So that's just what we empirically found. Okay. So so we can generalize any translationally invariant schedule of the subsystem toric code using this group homomorphism, and that gives us this depth 4 circuits. Another nice feature is that it has no hook errors. So any single circuit fault in your parity check measurement schedule results in at most one data key fault in the code. And that's just thanks to the weight 3 checks. So that's as a result of the weight 3 checks. So that's inherited from the subsystem toric code. And so to the best of my knowledge, it's a first finite rate code that we're aware of that has an efficient parity check measurement schedule. And so I think it shows that it's important to tailor the code to the schedule as well as vice versa. So for example, it'd be a lot more difficult to schedule, say, a 6-4 subsystem hyperbolic code. Decoding can be done just like with the toric code. Each X or Z error anti-commutes with 2 stabilizers, so you can just decode with matching. So you repeat the measurements L times and use a different syndrome, and that gives you this 3D matching graph with time like.
I mean, but that's for well, I mean that would work for any graph, so also for the graph that corresponds to your hyperbolic codes, right?
Yeah, exactly.
Okay.
And because for 2D, we can just use matching. Yeah.
Okay, fair enough.
Yeah. And then this is just to show some notation for later on. This kind of more abstract notation of the matching graph I'll use to explain this some of the scheduling. Okay, which brings me on to schedule and use gauge fixing. So gauge fixing is when you commute a subset of gauge operators into the stabilizer group. So you essentially fix them as stabilizers, and it's been used before, for example, to implement logical gates, although we're using it to improve error correction performance. And so let's look at some gauge fixes of the subsystem toric code. So without gauge fixing, the X-type and Z-type matching graphs are both a triangular lattice, which has a threshold of around 6.5% with matching in perfect syndrome measurements, shown on the right. If you fix the X-type gauge operators as stabilizers permanently, then you obtain the hexagonal surface code, and this is a Z threshold of 15.9% and an X threshold of 6.5%. But now with this hexagonal surface code, you now have weight 6 stabilizers. You no longer have the check weight 3. This compares to the surface code of 10.3% threshold. And so if you look at the subsystem surface code and syndrome measurements shown on the left here, so each dot is a gauge operator check and each oval is a stabilizer check, and the errors are occurring on edges, and the X checks and the Z checks alternate. The values of the gauge operators are randomized just because the gauge operators don't commute. So if you're interleaving like this, then you can't use any of the gauge operator measurements as sort of syndrome bits. If you repeat the X or Z checks, then the gauge operators of different types still don't commute, but of the same do trivially commute. So you can temporarily gauge fix them as if they were stabilizers. So if you look at now the 3D matching graph, and imagine, say, if we wanted to tailor this to Z bias noise, you could repeat the X checks more often. And you're essentially gauge fixing into this good hexagonal sort of surface code, good in the sense it has a higher threshold, if you consider it just as a static code, with weight 3 stabilizers. And therefore you reduce the average node degree in stabilizer weight. However, your check weight is still always 3. So although you're fixing temporarily into these hexagonal surface codes, you never have to measure the weight 6 stabilizers directly because you're still on the subsystem code. So for depolarizing noise, we see that changing the schedule already improves the threshold. So it goes up from around 6.5%, 0.6% to 0.8% for circuit level depolarizing noise. And you can expect it to get some improvement for depolarizing noise, but only to some extent. So you have leaks between these bursts of checks, measurements. And so although the average check weight is lower and the vertex degree is lower, but because of these longer weights, there is like an optimal number of repetitions. So we find that beyond around 4 repetitions, the threshold does decrease again. For bias noise, there's a much more dramatic improvement. So repeating the X measurements significantly boosts the threshold. So you now have longer sequences where the X gauge operators are fixed as stabilizers. So as an upper bound, if you just measure only the X gauge operators, then you get a threshold of a circuit level threshold of 2.2% for bias noise. So that's 4 times higher than the surface code.
Can I ask a question about the previous slide?
Sure.
So, wait, what is the graph showing? And so it's showing some advantage in like changing the order in which you measure the Z and X stabilizers?
Exactly, yeah.
And so what is kind of the intuition into why this improves the threshold?
Sure. So the main intuition is when you're repeating these gauge operators, after the first repetition, you can treat them as a stabilizer temporarily. So you essentially have more syndrome information. You have lower weight checks, if you look locally in the lattice, the degree of the matching graph is lower, which improves the threshold. So essentially, yeah, you have more syndrome information and an easier decoding problem, effectively. The only reason that you wouldn't keep increasing more and more is because you've just got these longer waits between. Let's say you're repeating the Z checks, and your X checks have to wait longer. And furthermore, the first time you measure the next batch of X checks, you can't fix the gauge operators.
Okay.
So
okay.
for depolarizing noise, there's this trade. You only expect it to. You only want to sort of use a small number of repetitions to boost the threshold.
So you're saying, like, if you would wait a very long time, the errors of the type that you're not measuring would build up up to some logical operator.
Yes, essentially, yeah.
Okay. Yeah. Okay. I understand now. Thanks.
Yeah.
Can I ask about the vertex degree reduction? Like, just in these pictures here on the left, we seem to be increasing the average vertex degree. So where are we making the savings? Are they all in like the horizontal plane, or am I missing something?
Oh, sorry. Yeah, it's partly because the diagram's quite small. I think the edges are quite small. So basically, if you look at, say, this one here, you can see you've got degree 8 shown.
I see.
Whereas that reduces to, say, yeah, so the degree does reduce. This is actually kind of like a cartoon of the matching graph, where it's actually missing out some edges. Yeah, so the degree actually, this also might make it a bit easy to see. You can see here, in any given, if you just consider one time slice, and in that particular time slice, you've got degree 3 horizontally, and here you've got degree 6. In actual fact, you've got other edges that I haven't drawn. These are a result of the different circuit faults that can, say, be diagonal edges, so they can both in space and time. So I haven't drawn all of those, but yeah, the degree does reduce significantly. Yeah, and so go ahead.
Yeah, just a small question. I was just going through your paper earlier, but you said that you alter the stabilizer measurement procedure, like these changes that you're showing, I think. You're saying that you do them in software, and I wasn't really sure what this means.
Oh, yes. I guess that means that the actual interaction graph doesn't change of the stabilizer measurements, in the sense that all we're doing is we're changing the order in which we apply CNOT gates. Therefore, we don't need any change in hardware interaction, if that makes sense. So it is a change in schedule. So it's a change in software, but say, unlike switching to a different code, let's say you want to actually implement, say, the hexagonal surface code, you'd now wait 6 checks, which would be a high degree interaction graph in your hardware. So in software, I just mean you're changing the order of the measurements, but everything else can stay the same. The actual hardware can stay the same.
No, it is not just it is not just a different way of decoding, but it's like you actually like do change like when you apply which CNOT physically. Yeah.
That's true. So it's not just by software I mean control software. It's a change in control software of the device, but not just decoding. But you don't have to change the interaction graph.
Okay, awesome, cool, thanks.
And so it kind of quadruples the threshold for up to quadruples of the threshold for high biased circuit level noise. And that's thanks to both to the improved threshold of the hexagonal lattice and also the low weight checks, which means reduces the impact of circuit level noise. And then you can also look at what the performance is like below thresholds. This is for distance 26 subsystem surface code, and you've got a kind of a forward as a magnitude reduction. So this is actually showing some of the ZX. This is just showing the standard schedule for the subsystem surface code. The orange line is showing if you change the schedule, but then you just ignore the fact you can use gauge fixing. So if you repeat, say, the X checks, but then just don't use the fact that you can treat them as stabilizers. That's just to look at the impact of just the noise model. You're changing the noise model by changing the circuit. So that's just looking at that. And then if you then do treat the gauge operators as stabilizers, you can see you get a forward of magnitude improvement. So it's changing the schedule actually makes them, if you don't use the gauge fixing, it actually makes things worse. And that's because in the standard circuit level depolarizing noise model, idle errors are actually slightly worse than circuit errors. That's why things get slightly worse if you don't use gauge fixing. And then this is comparing the performance of the subsystem semi-hyperbolic code, a subsystem semi-hyperbolic code to rotated surface code. So each of these green lines is a rotated surface code. The legend shows the number of physical qubits. And these are all encoding 338 logical qubits, just because that was the block length. Well, that was the number of qubits encoded in the subsystem semi-hyperbolic code. And so you can see that for a target logical error rate, well, for this physical error rate of say 0.1 to 0.2%, the performance of a semi-hyperbolic code with around 18.8 thousand physical qubits has a similar performance to one with a rotated surface code with 81,000, and this is including ancillas. And it outperforms a similar rate, distance 6, rotated surface codes below around 0.43%, and gives a 4.3 times reduction in qubit overhead, as I said, around 0.1 to 0.2%.
This is
with circuit level depolarizing noise.
I don't quite remember the numerics that Nico did in his semi-hyperbolic paper, but this is did you already see a similar improvement of performance in these in just the semi-hyperbolic codes in comparison to the rotated surface code, or this is something that mainly comes from the subsystem? Well, I mean, I guess Nico didn't do any circuit level simulation.
Yeah, exactly. That's the main difference. So Nico did phenomenological noise.
Yeah.
I expect if you were to do circuit level noise on the same codes, I doubt you'd see the same improvement, just because I don't know if you could do that fault tolerantly.
Mm-hmm.
Yeah.
And when you say like circuit level noise, you mean like depolarizing circuit level noise, or like independent noise? Like or bias noise? What's the noise model?
For this one, it's just depolarizing. It's a standard depolarizing noise model. So each each C0 gate is followed by one of the 15 non-trivial Paulis with probability P. And then the same for measurement and single qubit operations.
Good, wonderful.
So if I understand correctly, there are like multiple patches of the surface code, but I guess you only have to simulate one. But then how is the logical error rate calculated if you have multiple logical qubits?
The logical error rate here is defined as the probability that at least one of the 338 logical qubits fails.
Oh, okay.
So it's kind of equivalent to the subsystem semi-hyperbolic.
Okay, thanks.
And also importantly, I mean, you can see the gradient of the lines is also, they're essentially parallel. So you'd expect the same overhead reduction for lower target logical error rates. Okay, and you can also just combine the two techniques. So you can apply schedule-induced gauge fixing, the subsystem semi-hyperbolic codes, and this is now with a circuit level independent bias noise model, looking just at an X schedule. So just measuring only X checks, and then you have this gives a threshold of at least 2.4% circuit level noise, and that compares to a threshold around at least 0.42% for depolarizing noise. So it actually saturates, so we don't know exactly what the threshold is, but just have a look at that. Okay, now that's all so far. It's for homogeneous schedules, but you can also look at schedules which are changed throughout the lattice. So you can apply a different schedule to different parts of the lattice. So we give an example that increases the distance of the planar unrotated surface code, subsystem surface code. So if you imagine these schedules where you apply a schedule called L0 to even rows and L1 to odd rows. So this is a schedule, so rather than just repeating ZX, you take these two different schedules, which both use 3 X checks for each Z check, but offset by 2 time steps or a few time steps. You end up with a 3D lattice. So for now, I've sort of switched it. So time is going in the horizontal direction just because they're to make space. But you end up with a 3D matching graph where now in every time step, if you just look at a single type, you've increased the Z distance by at least 50%. So you have kind of the good lattice, as it were, the hexagonal surface code, and then this one where you've gauge fixed half of the rows, and then this one where you've gauge fixed the other half of the rows. And so the distance throughout the 3D matching graph, if you look at the minimum weight path, that's at least a 50% improvement of Z distance compared to just the standard schedule or the homogeneous schedules. So there's potentially some improvement to be had in homogeneous schedules. And so, yeah, you're increasing the Z distance by making fewer measurements. We didn't simulate that. Other applications, it kind of gives another different perspective in understanding lattice surgery, because schedule-induced gauge fixing can be seen as a way of, I suppose, interpreting the decoding problem for lattice surgery, which is in other work been shown to be gauge fixed. And you can also use these subsystem codes as an ansatz to construct subspace codes, where subspace codes are just stabilizer codes with a trivial gauge group. Subsystem codes is trivial gauge group, so I just mean regular stabilizer codes. So if you permanently gauge fix in these different family subsystem codes, then you can construct stabilizer codes that might be, say, tailored to noise models where which are inhomogeneous in space, say. And this is analogous to done by some people in Ken Brown's group on 2D compass codes. So you could just do the same thing for these subsystem codes. So perhaps there could be some interesting subspace codes to explore there. So in conclusion, we introduce a schedule-induced gauge fixing technique, which improves the subsystem code error correction performance and increases thresholds 4.3 times for bias circuit level noise. Still work to be done, say, to compare this to the XZX and tailored codes below thresholds. And also there are plenty of ways to extend this by applying it to other subsystem codes and also generalizing to decoders other than matching. And of course, decoders such as unifying can just be directly applied, but for cases where errors aren't, or the error model isn't graph-like, it'll be interesting to generalize to that case as well. And then the subsystem hyperbolic codes are these finite rate quantum LDPC codes with weight through checks and efficient schedule. And the first example of a code outperforming the surface code under second level noise, reducing the overhead by 4.3 times at 0.2% second noise. I think it's a coincidence that it's 4.3 times in both cases. And so more work is needed to show the advantage being retained for performing logical operations. So that goes back to a question, Jens, you had at the beginning. So this is just for memory in what we're looking at considering this work. So at that point, are there any more questions before I move on?
Yeah, maybe you hinted at this kind of connection with these compass codes, which I didn't quite get. So I vaguely understand what subspace codes are, and also kind of know a bit what the compass codes are, but I didn't quite get the connection. Can you say more about this?
Yeah, so compass codes are just gauge fixings of the Bacon-Shaw code. And that can be useful for essentially the Bacon-Shaw code therefore provides an ansatz to construct subspace codes, stabilizer codes. Subspace codes, I just mean a stabilizer code that doesn't have it has a trivial gauge group. Compass codes are just different sort of permanent gauge fixings of the Bacon-Shaw code. And the reason that can be useful is, say, you might want, suppose you have some inhomogeneous noise model, you might want to say have lower weight checks in some particular part of the lattice, or you might want to say tailor its noise by ensuring that the X checks have lower weight. So that's the 2D compass code explores that sort of problem for Bacon-Shaw codes. Mm-hmm. So I'm just saying here that you can do exactly the same thing, but rather than with Bacon-Shaw codes, you can apply the same thing to subsystem surface codes and subsystem hyperbolic codes. And so I'm just saying that these subsystem codes can be also like an ansatz just to construct new types of subspace code that might be of interest. Okay. You could say the same thing about pretty much any subsystem code, but it's worth pointing out that these irregular tilings might be of use.
Okay, cool. Thanks.
I also have a small question before.
Sure.
So as far as I understood correctly, you sort of systematically subsystematize the surface code or the hyperbolic homological codes, right? In 2D. So is there a way of generalizing this to higher dimensional codes? Because it seems to me that as long as you have sort of a group that generates this tessellation, it might have some restrictions coming from the construction, like the only specific Schläfli symbols. But do you have an idea, or is your line of thought useful for also subsystematizing other codes in higher dimensions?
Yeah. So firstly on it, there's some recent work by Mike Vesmer and Alex Kubica on 3D subsystem toric codes, which is worth looking at. In terms of other generalizations, so we did look at that. So for example, we looked at seeing subsystemizing hypergraph product codes and 4T codes. The way we looked at that was a different way. So we looked at a different perspective of constructing these subsystem codes where you're kind of merging, you can think of it as merging vertices in the lattice. But we didn't manage to find the generalization that didn't kind of hurt the distance too much, essentially. So yeah, we looked into it, but we didn't find generalization to high dimensions that didn't lead to the distance suffering. But yeah, I think it's an interesting question, but not something we explored in much detail. If you're looking at the appendix of our paper, I don't think I've got slides on it. Maybe I do in the appendix. We did talk a bit more about this. But yeah, we didn't manage to maintain the distance. We didn't manage to maintain the distance for these generalizations.
Okay, cool. Yeah, that's good to know, because I mean, there are different perspectives one can take to attack this problem. And if you said, okay, so there's a naive approach to generalize this high dimension didn't work.
Yeah, so the other way, so the way I described how we construct them in this talk is by kind of triangulating this lattice. But you can also think of it as you're taking, say in the case of the subsystem toric code, you're starting off with a hexagonal lattice and you're kind of merging vertices of opposite faces. And then for the hyperbolic, there's a kind of an analogous construction. So yeah, there's a different perspective you can take to construct them, and that might be more fruitful for generalizations beyond 2D. But yeah, as I say, yeah, don't explore it too much.
Do you think this on the scheduling part? Do you think a similar trick as you're doing for the 2D codes? Like, I mean, you're basically using your knowledge about how you schedule 2D toric codes or 2D subsystem toric code to schedule the hyperbolic variance of this. Do you think so? Say I had a 3D toric code and I had a schedule that's valid. Do you think I could use the same to go to 3D hyperbolic or?
Yeah, I think that'd be interesting to explore. Without trying, I don't know, but I'd expect so. I'd expect that would be. I think it's definitely worth a useful tool to use when exploring generalizations like this. In the case, I should say, in this case, the fact that it's a subsystem code is important. So for example, you can't directly apply the same method to schedule just to stabilize a hyperbolic code, maybe I think with some adaptations perhaps. But that's your, it's kind of convenient in this case that these gauge operators have this one-to-one correspondence with elements of the proper symmetry group. Yeah, no, I definitely think it's a useful tool to explore in other contexts as well. But we don't have we're not claiming some kind of general tool that will always work. But yeah, I think it's just a useful tool to consider when scheduling. But yeah, I think it'd be interesting to explore definitely for these high dimensional codes.
Yeah.
And then the other, so I haven't got a huge amount of time, so it's like 10 minutes. The other paper I was going to talk about is this one, which is not very closely related, but there is a connection. And this is on looking at optimal local unitary encoding circuits for the surface codes. This is work with these co-authors at UCL. And so this is a kind of more, the problem we're looking at here is encoding circuits for unknown states in the surface codes. And so what do I mean by an encoding unknown states? This is a circuit, a product state of k physical qubits and oscillators to the same state of k logical qubits encoded in an NK stabilizer code. And so the circuit should map the group ZK to Zn-1 to the stabilizer group, and then map the single qubit logical operators to the logicals of the code. And we focus on encoding circuits, which each gate is both unitary, geometrically local. So this is with respect to the interaction graphed by the stabilizer generators of the code. And so prior to our work, there are a couple of, hadn't been too well studied, but there was the best known local unitary encoding circuit for the planar surface code had a complexity of order L squared in the Dennis et al. Paper. And there's a log L complexity non-local unitary encoding circuit for the toric code. And so we were interested in exploring, it's known that there's a lower bound of linear of order for encoding planar code. So we were interested in seeing, can we find optimal local unitary encoding circuits that match this lower bound that Bravi found. And so if you can encode these toric and planar codes, there are actually uses to this because they can map firstly to other stabilizer codes. So for example, the subsystem surface code, that's the connection, is an order 1 mapping to the subsystem surface code, and also to the color codes. But we also, as I'll get on to, show that these encoding circuits can be useful for encoding fermion to qubit mapping, so for sort of state preparation and quantum simulation algorithms. And so in this work, these bits are the encoding circuits that we find. So we find these linear encoding circuits for the planar and toric codes, a linear encoding circuits for the 3D surface code, and also explicitly show the mapping to the compact fermion to qubit mapping, which is a recently proposed fermion to qubit mapping. So yeah, the prior work on local unitary encoders was this one introduced by Dennis et al. And it requires of order L layers of CNOT gates to increment distance from L to L plus 2. So shown by this little animation on the bottom right. So each layer adds a constant number of qubits.
And the quotation number 2 is that it's a kind of oh yeah, I see, because you mean you have to be order L to have topological order in the first place, right? I mean, any circuit must be of that size from the Lieb-Robinson bounds perspective. Yeah, sure.
Yeah, exactly. Yeah, so that it's Bravi's Lieb-Robinson bounds. That gives a lower bound.
Yeah, I mean that applies to time evolution, but of course you can also apply the similar argument to the gate setting.
Yes. Yeah, exactly. So that provides a lower bound of linear time, but the best known circuit was quadratic in L. So we were curious as to whether we could find some optimal circuits. Another encoding circuit for the toric code, this is the toric code, not the surface code, is the renormalization group encoder. And this was introduced by Aguado and Vidal. And it's unitary but not local. And here, essentially, the toric code is fine-grained. So you can start with some distance 2 toric code, blue at the top here. And then you can fine-grain it distance 2L toric code of order 1 time steps. But because of this fine-graining procedure, it's not local, but it does have log L time.
I mean, it's a stupid question. There was this work by Martin Schwarz and Toby Kubit and others on like preparing topological PEPs on a quantum computer. And I mean, the surface code or the toric code for that matter is also a PEPs, right? It's a bond dimension 2 PEPs. So applying those techniques to the surface code, do you know what would come out? I mean, how efficient that would be? Because this it's quite interesting, and I haven't seen this followed up so much in recent years.
Yeah, I'm not sure. I should be able to send me the link to the paper. Actually, that'd be interesting to look at. But I'm not sure.
Yeah, I sent you the link. Yeah, because they had been thinking about preparing PEPs and then preparing topological PEPs specifically, G-injective PEPs. But I mean that the toric code is a G-injective PEPs, the Z2 injective PEPs. So in this sense, that procedure should apply to your code in principle. Although I'm not quite sure what the scaling is, but it might be nice to compare.
Yeah, that'd be interesting to compare.
Be able to do better than log L from a complexity theoretic standpoint, because there are these. I think when was it? I think this paper was presented at last QIP as well, like complexity of stabilizer states. Or no?
Do you mean this reference 2 at the bottom here, the quantum depth lower bounds for homological codes? That does provide, that provides a lower bound of log L for the same problem. Yeah.
No, it was a bit more general. Like the paper I have in mind is, I think, called complexity of ground states of local stabilizer Hamiltonians. And and their result is that if you include like tracing out or measurements of ancillas, then there's sort of order log of the distance of the corresponding stabilizer code as a bound to prepare the corresponding ground state, which would in this case translate to preparing the code state. And I think that this is exactly where
wait, but this unitary encoding, no measurements.
All right.
Yeah, this is for unitary.
But it's not unitary because the setting I was considering allows for non-unitarity as well by like tangling ancillars and then measuring them out. But they don't assume locality. So
yeah. So
on stabilizer codes, and they are logarithmic in the distance.
Right. So for unitary circuits, there is this log L lower bound, and it was matched by this Aguado Vidal paper. But for I'll get on to for non-unitary, you can use stabilizer measurements. But that's so there's a paper by Lee et al. For magic state injection, which I'll mention later on. Okay, so the first first way we show of getting an optimal local unitary encoding circuits is pretty simple. You basically just apply if you just use a sorting network to the renormalization group encoder, it turns out that's already actually enough to achieve an optimal local unitary encoding circuit, albeit not a very good one. We improve on it. So just use C0 gates to essentially spread out the qubits in this fine graining procedure. Then the actual renormalization group step takes of order steps. The sorting network takes of order L, and so that leads to a linear time encoder for a distance L torus code, but with a larger than necessary constant of say 15L/2, and this is for the torus code. So we're just curious as to whether or not you could do better, and also whether or not how to apply this for the planar code. And there's a sort of a simple circuit to obtain a linear complexity encoding circuit for the surface code. And so we find a circuit which encodes a distance, increase the distance by 2 using 4 time steps, which leads to a 2L complexity encoding circuit for the planar surface code, which matches a lower bound by Bravi, but with a better constant than our other method. Worth noting that you don't always have to map the generators to minimum weight generators. We just have to map the group. So in this particular circuit, we're mapping these weight 4 generators to weight 7 generators, but the group is still generated by the correct stabilizer group is still generated by these, and we generalize it to rotated angular codes. And we can also find circuits, generalize this to toric code, so we can map between the surface and the toric code, therefore using the RG to generate surface codes, and also look at dimensions. So if you imagine, say, a surface code in the XY plane here, there are also, we find encoding circuits that can then generate a 3D surface code from that. Although we leave kind of higher dimensions to future work, we don't prove the same thing, but we expect the same method could just generalize to higher dimensions as well. So giving optimal encoders for those. Okay, and the question is, why not just use stabilizer measurements to encode linear states? And indeed, say for magic state preparation, you would do just that. However, it can still be preferable in some circumstances. So firstly, NIST devices only support local unitary gates, not stabilizer measurements. So if you just want to demonstrate, say, topological quantum order, then it's better or easier to use an encoding circuit. You also save a factor of 2 from ancillars. And it's also useful for demonstrating topological quantum order. And furthermore, encoding circuits for the surface code can actually be useful for state preparation for stabilizer-based fermion mappings. And in particular, the one example that we look at is the compact mapping. So fermion to qubit mappings are essential for some quantum simulation algorithms. They define a representation of fermionic states as qubit states, fermionic operators as Pauli operators. And the compact mapping of Darby and classes are particularly good parameters. And it's already known to have a similar stabilizer structure to the surface code. So we can show that explicitly here. These weight 8 stabilizers are very closely related to the surface code. And so this is a natural application of these encoding circuits. Since you have, we showed there's an order 1 circuit to encode the compact mapping from the surface code. As this could be useful, say, for state preparation and quantum simulation algorithms, where it likely wouldn't be, it'd be much more preferable to just use a simple linear time encoding circuit than, say, state preparation and decoding, than stabilizer measurement. And also there are other stabilizer-based fundamental qubit mappings like the Serac mapping that also have a similar structure to the surface code. So it may be that this is a promising route for state preparation in various different stabilizer-based fundamental qubit mappings. Okay, so in conclusion, we found optimal local unitary encoding circuits for 2D and test codes, which is a quadratic improvement on prior work. Can be useful for encoding fermionic states and fundamental qubit mappings. And it's sort of a more efficient way of demonstrating topological order. And on, I have to take any other questions.
Okay, cool. Thanks.
Wonderful. Let's chat first. Thanks for this very inspiring talk with lots of food for thought and ideas and things. That was great. Yeah, we had lots of questions already, but I'm sure there's more questions. So let's have questions. Who goes first?
Yeah, I think I just have a brief question back on this on your scheduling thing for the subsystem codes. Can you, like, given a general hyperbolic, I mean, just a general hyperbolic surface code where you don't want to look at the subsystem variant, is there a way to, I mean, can you use your scheduling trick to also schedule like just normal stabilizer code versions of these?
Yeah, so we looked at that. Yes and no. So I mean, yeah, so in the appendix, towards the end of the appendix that we do discuss this, it's not so straight, you can't use directly the same approach. I think that using these homomorphisms would be useful. But the slight difficulty is you kind of one ancilla shared between all qubits in the stabilizer. So the nice thing about the code is it kind of breaks up the breaks up and kind of parallelizes the circuit, which makes it a bit simpler. So yeah, we do discuss this, and we actually talk about the constraints that the ancilla in a stabilizer variant of the hyperbolic code imposes on the homomorphism and the symmetry group. And we did enumerate the different groups that might be useful for that. So yeah, that's in the appendix to the paper. Okay. But we didn't explicitly construct circuits from that and then or simulate them. But we just discussed it. I think it's definitely more straightforward for the subsystem ones, just because you're kind of the way it breaks up the that kind of allows you to parallelize, and yeah, you don't have to worry about this. Yeah, there are just less constraints essentially on the circuit. So yeah, it's mainly most effective the subsystem ones, but I definitely think it would be useful for scheduling subspace codes as well.
Yeah, and okay, and the other thing is that also on the scheduling, like so here use this trick to basically map the scheduling approach for flat toric codes to hyperbolic ones. But all you needed was degree 4, right? So in general, I could just, no, you need that it is regular. Okay.
Well, the regular actually, so once it doesn't need to be regular, because you can use, we show that provided the schedule is valid for the standard hyperbolic tessellation, then turning that same compactified tessellation into a semi-hyperbolic lattice will also be schedulable, even though it's no longer a homomorphism, of course, because it's an irregular lattice, so it no longer has a symmetry group. But yeah, if you use that trick to find the schedule for regular tessellation, then yeah, the semi-hyperbolic tessellation will admit the same schedule. You schedule it, you generalize in the kind of the obvious way of using the same, but it's no longer a homomorphism.
But if I just had like some completely random, say even just a 2D, just some completely random 2D code, which might have a very weird structure, but say it still has the vertex degree 4, do you think you can still use this trick, or is it?
Yeah. So I think even if it doesn't have a group structure, you could still use a similar trick.
Yes,
but
you would have to like.
But I think
the vertices, so it's the edges. Sorry, it's the corners or something like that.
Yeah, but you'd probably get very lucky. You'd have to be very lucky with a random lattice to have that property. So I think the group structure isn't necessary, but it provides a more clear way of explicitly constructing lattices that are more likely to have the right property. Of course, the compactified lattice still has a chance of not working. But and another thing what else was I going to say? Yeah, I can't remember. But yeah. So I think for the stabilizer codes, it's helpful, but not immediately obvious. But yeah, for subsystem codes, it's definitely a useful tool for constructing schedules.
To ask a question about the last part of the talk. So I mean, how much of this encoding is really glued to the surface code or the toric code? I mean, similar ideas should also work for other, like surely for the color code and so on, right?
Yeah, actually, we didn't look at the color code, but well, I suppose for the color code, well, actually for the color code, you can just use our circuits and then there's already a known mapping.
Oh yeah, so no, that's right.
So.
Yeah, I mean that's all. It's rather straightforward. And
Yeah.
then I mean, you mentioned these fermion to qubit mappings, like where you kind of made progress on the fermionic stage representation as qubit states and so on. But you seem to have like one specific fermion to qubit mapping in mind that's different from the Derby and Klassen one, and also for the Strata and Sirac one, which are like different encodings that would kind of represent the ground state properties of a fermionic system, right, with a qubit encoding. So like what can you learn about these different fermion to qubit mappings using your approach?
What can you learn about the mappings?
Yeah.
Yeah, actually already in the Derby and Klassen compact mapping paper, they already actually discussed the connection to the toric code there, or without providing encoding circuits. Yeah, and I can't recall. Yeah, so I'm not sure, and I can say anything too profound about the connection, but it is discussed in the similarity discussed in their paper.
Okay, nice, cool, thank you.
I have a question about one of your applications of the encoding circuits, like one of the motivations, what you can do without stabilizers. You say you can show topological order. What does this mean, and what would an experiment to show this look like?
Yeah, so that's actually been done. This was the Google team did this recently. So it was after our paper came out, and they did this for the planar surface code. And so I think I've got the
braiding of anions.
It's earlier this year. Yeah, exactly.
Okay.
So I recommend refer you to that paper. So that was recently. Yeah.
Okay.
I'll find the reference.
Yeah, I think I know the paper. We read it.
Yeah, this one. Yeah.
Yes. Okay. Thank you.
So I have another question on the scheduling part, because you mentioned that the group structure is not important, but you have other consistency conditions. So on this homomorphism, or that was a group homomorphism, your tessellation has this group structure.
So I didn't quite catch all of that. Could you say that again?
Yeah. So my question is for that slide. Yes. So you mentioned that if you have some random tessellation, you still have conditions that it has to fulfill in order for this trick, or for this method to work, to like map it onto C4 in this case. Could you elaborate a bit what these conditions are? I think I just missed it when you were talking to John.
Sure. Yeah, so the way to see this is, okay, what do we know? If we go back to this, so when we look at this translation invariant schedule, so let's suppose you have a schedule that is valid for this subsystem toric code. That means that let's say you have a gauge operator of type 2. And so every gauge operator labeled 2 has exactly the same schedule. all we have to worry about is we just have to look at the neighborhood of this operator. So the neighboring every gauge operator that it intersects with. These are the only gauge operators for which the circuit could for which we have to kind of consider whether or not the circuit is valid, whether or not we'll be measuring whether the circuit is valid and doesn't interfere with the other gauge operator measurements. So provided that our circuits, provided we've already verified that our circuit is valid for the subsystem toric code, which you will have done once you've got a valid translation invariant schedule, then you only have to verify that the neighborhood of any gauge operator is the same in your hyperbolic tessellation. The observation is that provided that you can verify that for each type, so let's say you look at each type of gauge operator, you have to verify that the neighborhood of that gauge operator, the gauge operator it intersects with, and therefore the gates in the circuit which it might anti-commute with or not commute with, you just have to check that they are consistent with your hyperbolic tessellation, and then you know that your circuit is valid. Here, going back to the subsystem hyperbolic code, provided you find this valid labeling, which satisfies this group homomorphism, then we show that basically the neighborhood of each of these gauge operators is identical to that of the subsystem toric code. So you've got 4 different types of schedules, 4 different types of gauge operator, and for each one, the neighborhood, the type gauge operator and its orientation and relative to the gauge of interest is the same in the hyperbolic as well as the subsystem toric code. So these are the constraints. This is what I mean by this is how we ensure it's valid, just by ensuring that the neighborhood of every gauge operator is the same in the subsystem hyperbolic code as in the toric code. But rather than using translational invariance, where you're just looking at, say, one face of the lattice and then just translating it, and once you know that one face is valid, then you know the whole lattice is valid. Here we're saying that once you know some small patch of the tessellation is valid, then by this group homomorphism, we know that the whole tessellation schedule is valid. And yeah, so another way, let's suppose it's not, sorry, go ahead.
If you don't have a translation invariant lattice, like what is the domain of the F of the map F?
Mm-hmm. Yeah, I was wondering the same thing. Mm-hmm.
Like, because it's quite important, as I understand, that the domain is a symmetry of the lattice, right? Or like that it has a group structure on it in this particular case.
Yeah. So this is a map from the translationally invariant the rotation. Orientation preserving symmetry group. So it's a map from the orientation preserving symmetry group of the lattice to Z4. So this group. So it's a group generated by rotations around the faces and the vertices. Symmetry group.
I see. So that's what you have for your for the subsystem surface code schedule.
Mm-hmm. And then the same.
Yeah, and then you map sort of your I don't know, your symmetry group of the hyperbolic tessellation to the Z4 by a homomorphism. Right? But if you don't have this same symmetry on the level of the tessellation, how are you guaranteed to be able to map it onto Z4?
Right. You're not guaranteed to get it onto have the homomorphism to Z4. So that's why you're restricted to, say, 4K for tessellation. Well, that's why examples include 4K4 tessellations, but not others. This f of rho equals f of sigma equals 1 constraint. This just defines what I was talking about when I was referring to sort of the neighborhood of a gauge operator. So this is just saying that if you rotate around a vertex or a face by 1, then you're incrementing the label by 1. And that fully describes the neighborhood of each gauge operator. And therefore, since that is preserved from the subsystem toric to the subsystem hyperbolic codes, since this is the same, this condition is the same for the subsystem toric and subsystem hyperbolic codes, that means that the neighborhood of each gauge operator is the same in both cases. And therefore, if the first is valid, then the latter is valid. And then so the group homomorph. So if this is therefore the definition of a group homomorphism from this orientation preserving symmetric group to Z4, then you know that you've got a valid schedule, provided this has degree 4. So it's a tool to help check that it's a tool that can be used to construct valid schedules, but it's not, you don't just use it in isolation. Additional constraints, such as the lattice has to be degree 4. And additionally, you can also apply it to irregular lattices as well. It's just, as I say, it's just like using translation invariance. It's just a useful tool for constructing schedules. Mm-hmm. Does that make sense?
I think in my head I confused this checking the validity of the schedule and the construction of the schedule. So, and I see how like the group structure of G plus RS helps a lot in checking the validity. I think I understood now that you can also use the same construction for other tessellation, but then you won't have the same argument from its validity, but it will still be valid.
Yeah.
Okay.
But you can still just check. You can still just try coloring the lattice. Essentially, you can still just try incrementing by 1 mod 4, coloring the corners and see if it works consistently with a kind of a breadth first search. So that's a brute force way of doing it. But with the group, theoretic argument, then you can just look at the presentation of the group and see immediately whether or not it will work. And you can, it also provides insight into what other symmetry groups might admit these schedules. So, but yeah, certainly not.
Probably Baroque, right? I mean, that's your case is probably the only one that leads to relatively low weight stabilizers, or not?
Sorry, as the only one that leads to what? Sorry.
To lead to rather low weight stabilizers. I mean, this 8-4 tessellation is basically all there is, right?
Yeah, you could go to 12-4, but yeah, there wouldn't be
okay.
Probably wouldn't be much point. Yeah.
So if I may follow up on my previous question, when you I mean, the most practical application of these kind of encoding circuits for the fermionic states is that you can actually prepare fermionic states in the compact mapping, right? So that gives rise to a nice procedure. Is there also an optimality claim coming along with this? In that you basically have like an optimality claim for the surface code, and that you are order L in your encoding circuit, and you can't be any better. So up to constants, you're kind of optimal. Does it also apply to these fermionic state preparations that you're in some way optimal? And another question is that could you also like incorporate like further locality constraints in the construction, or is that really not so obvious?
Yeah, so for the fermionic mapping, yes, it should be optimal since since there's an O of 1 mapping, since there's an O of 1 local unitary mapping from the fermion to QMIO mapping from the compact mapping to the surface codes. Therefore, there cannot be a more efficient mapping for the compact mapping. Otherwise, you could use it to encode the surface code more efficiently.
That's right. Okay, that makes sense.
For the enforcing additional locality constraints, can you elaborate on what do you mean by that?
Oh no, I mean you have a kind of you have an explicit encoding, but it could be that kind of you can only apply certain gates in your encoding. That's the kind of certain constraints on what types of gates you can locally implement. I mean, there's lots of discussion on do like non-physics agnostic encodings of certain code words. So can your approach be combined with like constraints of that type of what like on locality or what gates you can implement and so on?
Because we don't look at other constraints. I mean, imagine mapping. I guess you could imagine compiling the circuit to some other constraint, but we don't look at those methods or whether or not, say, compiling versus just coming up with. Yeah, we don't look at. But no, you certainly could. I mean, aside from kind of the obvious kind of immediate applications of say compiling, we didn't look at other constraints.
Okay.
Can I ask a horribly vague question about your second work? So if I'm interested in doing state injection as fault tolerantly as possible on some logical computer, what can I learn from this paper?
Right. Yeah. So that's of what you wouldn't use it for.
Right.
So for that,
Yeah.
So for that, you already need stabilizer measurements.
Yeah.
So there's
exactly.
in that case you just use a fault tolerant protocol such as the Lee. Oh no, other Lee. Sorry, I probably cited. I think towards the end. I'll just find the paper, the reference. Yeah, this one. So I'd recommend reading. I mean, maybe you've already seen this paper, but
I have.
That would be a more appropriate.
You reckon there's nothing to be gained from your new approach? If I'm
sadly not. No.
Okay.
Yeah, the constraint for local and unitary gates does not apply when you're already natively able to implement the stabilizer measurements. So.
Okay, cool.
Yeah, so there are advantages for implementing these states on say NIST devices where you might want to save, you might not want to use ancillas, and you might want to say you might not have stabilizer measurements, and also for the encoding circuits where again you might go for the fermion to QMIO mappings where again you may not want to be using stabilizer measurements and decoding. But yeah, certainly for state injection in that regime, you really should be able to implement stabilizers, measure the stabilizers straightforwardly. So you want to use a fault tolerant protocol like this one. Yeah.
Mm-hmm. Excellent question. Are there more questions?
Can I pivot from a vague one to a really specific one?
Please do.
In your first paper, it's just me being a bit thick, I think. I was confused when you said if you've got schedules that involve ZZ, you can use two ancillas to parallelize these measurements.
Oh, yes. Yeah.
Could you explain that? I was a bit lost there.
Yeah. So we looked at two different. So you can use. Actually, I think it might be in the appendix here. I've got. See if I can go through fast enough. Essentially, you can remove idle time steps, adding an additional ancilla. When we look at the below threshold scaling, we don't do that. We include the idle time steps. When I showed you the kind of the 4 orders of magnitude improvement in logical error rate below threshold, we only use a singular. But if you want to maximize the threshold, let me find it. Then you can use 2 ancillas per gauge operator to kind of pack the schedule as tightly as possible. Essentially, this saves you, because the state preparation and time step, the state preparation and measurements take up time steps, unless you add unless you parallelize essentially with an additional ancilla, you can't pack the schedule to be maximally deparallelized without any idle time steps. But you can just use a single ancilla and we still see kind of a big increase in threshold. And when we look at the below threshold performance, we just use a single ancilla. So I think, essentially it's just a way of trading off. You're trading off by adding additional ancillas, you can increase the threshold and remove idle time steps. It just means that otherwise you can't apply a CNOT gate while you're saying, let's say you've you've measured this gauge operator once. You can't start the next round until you finish measuring this ancilla. So if you introduce a second ancilla and parallelize, then you no longer need to wait essentially. So you can remove idle time steps from the circuit, but you don't need to do that. You can just use a single ancilla. So we simulate both, and we see an improvement for both, but you can boost the threshold a bit further if you include the ancilla.
Okay, so what should I understand by the notation where I've got a pair of numbers? I was a bit confused by what.
Means. Sorry. Yeah, that's so that just means I'm considering 2 consecutive rounds of measurement.
Yeah.
And these numbers are all mod 4. Or
yes. Okay. But then
so
if I'm
that should be a 0. Yeah.
So that one that your mouse is on now, is that saying in the first round this is measured in time step 3, and in the second round it's measured in time step 1?
Yeah, exactly.
But then if I parallelize that, and I think this is why I'm being stupid, the second one seems to come first if I parallelize with it.
Second one. Sorry, the second one comes. Oh, these are modular.
One is lower than 3.
Yeah, but they're modular. It's a periodic. So.
Okay. So the parallelization is not that. It's
Yeah, so I think the easiest way to see it is if you just look at this this data qubit. Look at this data qubit here.
Yeah.
Actually, let's look at this one.
Yeah.
Yeah, maybe. So look at this data qubits. This is on the original schedule.
Yeah.
You can see that there is no idle time step. You've got
Yeah.
this. You say identify this one with this one.
Yeah.
In time step 0, 1, 2, and 3, there's always a CNOT gate acting on this data qubits.
Yeah.
And the same here, if you just consider, it's not the clearest diagram because we put quite a lot of different, we put two same diagrams. I mean, you should only consider only the red one or only the blue one at any one time. But effectively, if you look at, say, this corner here, you can see that time steps, this is acted on in time steps 2 and 4 by this CNOT gate, and in time steps 1 and 3 the CNOT gate. So there is no idle time step.
Right.
But these are only 2 time steps apart. But this oscillar needs at least 4 time steps to measure this whole gauge operator.
Okay. Cool.
If the state preparation and measurement takes 1 time step. So that requires 4 time steps, and then you've got these are 2 time steps apart. So you need the extra ancilla to parallelize. However, you can just use one ancilla and just add idle time steps, and that's what we did in our simulations for the bone virtual scaling, and we still see a big improvement. So you don't need to parallelize like that. So if you wanted to use fewer qubits, you could just use ancilla. In that case, your schedule is just exactly the same as the standard schedule, except you just don't implement the gates, some of the, say, X gates. If you're doing a Z, let's say you're repeating X checks, you would literally just remove some of the Z checks.
I see.
And so removing gates in your schedule actually improves the error correction performance, even though you're adding in idle time steps instead, which have a higher error rate. Which
is kind of counterintuitive somehow.
Yeah, you're doing less work, but you have a very big improvement, and the reason is because you're no longer ruining your gauge operator. You're no longer measuring these anti-commuting operators. So by removing these Z checks, gain much more syndrome information about the X checks. So measuring the Z checks is actually hurting your performance.
I see.
Yeah.
Interesting. Yeah. Now that you say it, it makes more sense. But at first it sounds a bit counterintuitive.
Yes. Yeah. Definitely.
You mentioned like in the first part that this kind of schedule-induced gauge fixing can improve the decoding for like instance of measurement-based logical CNOT gates. So what's the connection of your approach to these measurement-based logical CNOT gates with? Because I thought you were like explicitly not considering this in your approach.
That's true. This is just looking at lattice surgery for standard subspace surface code. So just the surface distance, let's say the rotated surface code. And there was a paper by Christophe Rio and Ling Lau and others, trying to find the reference, and showing how lattice surgery can be seen as gauge fixing. So you can consider a larger subsystem code, which lattice surgery is gauge fixing. So the observation is that you can look at the decoding problem of lattice surgery from the perspective of schedule-induced gauge fixing, and use similar methods of constructing matching graphs. I haven't seen too many details on exactly how. I think there are different approaches to decoding lattice surgery. So it's more of a different perspective on decoding. So you can use the same kind of same difference syndromes. You can use the same definition. The different syndromes we introduce here to decode lattice surgery in the rotated surface code. But yeah, it's just a different perspective. I'm not entirely sure whether. I think the details of how people decode, say, in surgery, often they're not given in full detail in papers. So I don't know if it's what people have already kind of worked out.
Fair enough.
Decoding in the past. It's just a different perspective. So I think it's only recently that there was this work kind of explicitly showing how lattice surgery can be seen as gauge fixing, but they didn't advantage of that in that paper for the decoding. So they still treated all the gauges just as gauge operators, not as stabilizers. So the observation now is just that you can gauge fix the gauge operators and then use this difference syndrome to switch between different sort of sections of the lattice graph.
Okay.
But we don't quantify any improvement there or compare.
Yeah, that's very difficult, as you say. I mean, it's a bit, it's hard to compare to other approaches because, I mean, it's not so explicit most of the time. Wonderful. Cool. That's great. Wow, we had lots of questions. Is there a final question from the big office, maybe?
Final question. No, I don't know. Not for me.
I also don't have any more questions.
Good. No, that was really fun. That was great. Thanks for this. For this ride through the world of surface code, subsystem codes, and optimal encoding circuits. And also this hybrid format worked quite well. So how was it in your office? In the big office, this worked well, no?
I'm seeing not so.
Question is, how good is it with the audio? Somebody edits besides Jonathan talks. Yeah, you're not. I mean, you're audible. It's not fully perfect, but it's fine, I think.
Okay, cool. So
Good. Cool.
Oscar again.
Yeah. Thanks, Oscar again. That was absolutely wonderful. Thanks for this inspiring talk. Also for allowing us to record it. Let's catch up soon, Oscar, on this. Yeah, thanks for all the wonderful questions and the discussions. And again, Oscar, for this wonderful talk. Great.
Thank you very much for the invitation and for the questions. Yeah.
Yeah, great. Thanks. And have a good rest of the day.